Yeah, so last time we talked about the evolution of the sun. I'm going to go over it real fast, and then I'm going to get into evolution of more massive stars, like the evolution of the Bob the Builders, the O stars, B stars, and A stars. O, B, those guys. And so let me just go over the evolution of the sun real quick. I'm not going to show you just images. I'm just going to do it by my hand. So we said that the sun starts evolving when the hydrogen in the core runs out, right? There's a couple of things that we should know. One is that every time a star collapses, right, then temperatures go up. When temperatures go up, most of the time you're burning the next element. You burn like if you hydrogen runs out, then the star collapses until the temperatures are high enough for a hydrogen shell or a helium core to ignite. And then the star expands, right? So it happens all the time. Now, with the massive stars, it happens even more because they have so many different cores, multiple shells and cores and stuff. So that's going to be kind of a little bit complicated, but I made a whole bunch of little drawings for you guys, so hopefully they'll help you. All right, so now when the sun's hydrogen is depleted in the core. Why do I say depleted? Because it's not all gone. It's just not efficient enough. Like maybe even if 50% of the hydrogen is depleted in the core, then you don't have enough hydrogen to survive. And so your survival is based on how much energy you make in the core. This energy comes out and it supports your upper layers. If you don't have enough support for the upper layers, then the star will collapse, temperatures go up until you find the support, then you make energy, then the star expands like that. So you could continuously do that. So for the sun, this happens when the hydrogen in the core is depleted, the sun collapses, the hydrogen surrounding the core that is virgin, is untouched, that starts burning. When I say burning, it means fusing. So that hydrogen in the shell starts fusing. When that happens, there's so much hydrogen outside of the core than used to be in the core. So then the sun expands to become a subgiant. And then the hydrogen in the shell is going to be depleted. Then it collapses again. Collapses again, temperatures go up to 100 billion degrees. At 100 billion degrees, you can fuse helium. So the helium core ignites. And within just a few minutes, the sun starts getting bigger and bigger and bigger and bigger. It's going to become a red giant now. It's going to become like 100 times bigger, no time. And so this is the red giant stage. Now, when the red giant stage comes and you're making so much energy with your helium core and your hydrogen shell, you're losing a lot of the mass on the outside. So a lot of the mass, the ones that are very easy to dislodge, they're going into space. So there's going to be a huge cocoon of gases surrounding you, and those are expanding away from you. Eventually, it's going to be a big cocoon that we call a planetary nebula. Now, at the end, the helium in the core has turned into carbon. So helium fuses into carbon. Now, carbon requires 1 billion degrees to start fusing. The sun never reaches carbon fusion temperatures. Maybe a little bit, but not much. So the carbon just stays put. Then at this point, when you have an inert carbon core and the helium shell and the hydrogen shell are depleted, the sun collapses and collapses and collapses and collapses until it becomes like a million times more dense, and it becomes a electron gas. Basically, electrons dominate, and this electron pressure that builds up, when the electrons become degenerate, it forms electron pressure, and that pressure stops the sun from collapsing. We call this object a white dwarf. And so a white dwarf has like a carbon core. It has degenerate matter that you can't compress anymore, mostly electrons. We said electrons act kind of like a solid liquidish kind of a thing, and very, very strange. Nowhere in the universe is there anything like it except inside of a white dwarf. And then that's the sun's death. The white dwarf has so many electrons that it's kind of like an electric star. So the energy is dissipated from inside towards the outside by conduction. It's the only star that uses conduction to move energy. And then it becomes a black dwarf. Now, how long it takes it to become a black dwarf, nobody knows, because the universe is only 13.8 billion years old. And a white dwarf takes something like 1 trillion years to become a black dwarf. So we have no idea. We've never seen a black dwarf, but I'm sure they exist in the future. And that's it. The sun is dead now. It's the corpse of the sun. It kind of fizzled out. Nothing biggie happened. Now, in the O, B, and A stars, which are much more massive, you're able to go beyond carbon. You can fuse carbon, no problem. In fact, you can fuse everything up to iron. Everything up to iron can be fused inside of a O, B, and A stars. So let's go into it. Let's see. I'm going to go slowly and try to follow exactly what I'm saying, please. So this is a core of an O, B, and A star. So outside of here is the star itself. Here we have, let me get this nice little, okay, there we go. Outside of here, there is a whole bunch of hydrogen that is unused. Here, hydrogen is under tremendous pressure and temperatures, and this is where all the energy building is going on inside of this massive star. Now, in the massive stars, hydrogen gets fused into helium faster and more efficiently than in the sun. They use something called the CNO cycle, carbon, nitrogen, oxygen cycle, to enhance the hydrogen fusion. So it burns hydrogen like crazy. Now, all stars die very quickly, like in 5 million years. 5 million years, the sun dies in 10 billion years. So the difference is gigantic. In fact, the more mass you have, the faster you go through your energy sources. So this O and B and A stars, they die very quickly. The one that lasts the longest is the A-type star. A-type stars last something like 500 million years. That's a half a billion years max. That's it. The rest of them, like O and B stars, they go quickly. But they're Bob the Builders. They give up the entire, they give us the entire periodic table of the elements. Everything, that's why I call them Bob the Builders. So, like I said, we've all been inside of an O, B, or an A star. All of us here, we've been there. Our atoms come from there, right? Because the sun is not capable of making things like iron and nickel and what else is in our blood, you know, everything that is in our body, all this stuff was made inside of a very massive star. And it could have been maybe not just one, maybe 2 or 3 generations ago, son's mother and then father and all that. And so, Mina, are you there? Mina?
Yes.
Can you read this?
The star has a span. Yeah, I can. Should I do that?
No, I just want to make sure that you read it because I wrote this her for you.
Oh, thank you.
Okay, that's right. Okay, all right.
You know, in my childhood, childhood story, they always call the sun as a woman. You know, Farsi, they call it
Uh-huh.
Khurshid Khanum. So
I see.
that's
Yes.
why.
Well,
Yeah.
here they say the moon is a female and the sun is a male. It's a little different, but you know, every different culture has different, stories. No worries. Anyway, so this guy lasts not very long, but the hydrogen in the core very efficiently keeps the upper layers from collapsing. That's the job of this energy. So the energy that you produce in the core keeps your upper layers from collapsing because they're balls of gas. And these balls of gas would collapse if you leave it to themselves. All right, so now, first thing that happens, number one thing that happens when these guys go to evolve is that hydrogen in the core has depleted. So the upper layers do collapse. Temperatures do rise. Now, when the temperatures rise, there's hydrogen outside of the core that is untouched. This hydrogen outside the core that is untouched is now ignited. Not the core itself, which is helium now, mostly helium anyways. There's some hydrogen, I'm sure, mostly helium. But in this case, when the temperatures go up, the stuff outside of the core that was just untouched and virgin is now going to be ignited. So we're going to have a shell of hydrogen that's going to give us a lot of energy, more energy than we were getting from a hydrogen core. Hydrogen shell that has a lot more hydrogen to burn. So now the star expands, right? The star expands big time. Now the core here is inert. Helium is not burning yet. So what's the next thing that happens? Well, the hydrogen in the shell eventually will be depleted. But at this stage, the star is huge now, just with the hydrogen core. We call this star, when an O, B, and A type star have evolved, we call these stars red supergiant stars. All right, so a red supergiant star is one of those freakazoid stars. These freak stars are going to be huge. Some of these are as big as the orbit of Jupiter. Now, some of the really big ones, like the ones that have 250 times the mass of the sun, I've never seen one, but I'm sure they exist. These guys are called hyper red hypergiants. So they become as big as the solar system, gigantic things, unbelievably huge, like a
Can I,
thousand times the size of the sun. Yes.
um, okay, actually have two questions. So all stars have hydrogen as their very core.
Correct.
Okay. And I forgot the second. If I think of it, I'll let you know. Sorry.
Yeah, no worries. All right, so far we have the hydrogen in the core being depleted, just like the sun. Again, the star collapses until temperatures go up, and the hydrogen shell in this case is going to be ignited. So our hydrogen shell is ignited. We make lots of energy, more energy than before. So this star expands to become a red supergiant. Now, what's going to happen next is this hydrogen in the shell is going to be depleted. So what does hydrogen turn into? It's going to turn into a helium. So the hydrogen shell is going to become a helium shell. And we have a helium core already. So when the star collapses, this helium core is going to ignite, and whatever is left over here in the hydrogen shell is going to be a helium shell. I'm going to have to change this slide. It's going to also ignite. So the helium core ignites, the hydrogen core ignites. We got this thing going on here. Lots and lots of energy. But the temperature has reached 100 million degrees Kelvin before helium ignites. So helium takes a long time to ignite. When it does, it requires 100 million degrees Kelvin. 100 million degrees Kelvin is the same as 100 million degrees centigrade. The difference is only 273 degrees. So big deal. We have 100 million degrees, give or take 200 degrees, doesn't make any difference, right? So you can imagine this is degrees centigrade. Now, helium in the core is going to ignite. When the helium in the core ignites, lots and lots and lots of energy are going to be coming out. The star gets even bigger. It's going to be a bigger red supergiant star. At this stage, when you are burning helium in the core, the helium turns into carbon. But carbon is not ignited yet. Carbon requires 1 billion degrees to ignite. So to fuse carbon, you need 1 billion degrees. That hasn't been reached yet. So when helium in the core is depleted, it's going to be an inert carbon core. No energy is coming out of the inert carbon core yet. So the star collapses. When the star collapses, then the helium shell and the hydrogen shell, they ignite. They burn for a while, and then, after just a few years, they're depleted. So the star collapses, and this time it goes to 1 billion degrees Kelvin. So now we're going to get the carbon ignited. So now the carbon ignites. So lots of energy comes from carbon burning or carbon fusion. Now a helium, we said, burns at 100 million degrees. Temperatures are 1 billion degrees in the carbon core. So it's also 100 million degrees in the helium shell that was left over from the hydrogen shell. So we have a hydrogen shell on the outside, a helium shell in the middle, and a carbon core. They're all burning simultaneously. So what is
Professor,
the
can you go
carbon?
back to the last slide? Sorry.
Sure.
Thank you.
You're welcome. All right, so here helium in the core is depleted and there's carbon in the core, but it's not burning yet. So it's going to collapse till the temperatures go to 1 billion degrees Kelvin. Now carbon ignites. So we have a carbon core, a helium shell, and a hydrogen shell burning. Alrighty then. So lots and lots of energy is coming out. The star expands and is doing great. This is a huge, huge star now. What do you think is going to happen next? Let me think about this. So what is hydrogen here burning into? Hydrogen here is burning into helium. What is the helium here in this shell burning into? Carbon. What is the carbon burning into? Well, the carbon is burning into neon. And so it's going to leave a neon core. And again, helium turned into carbon here. And hydrogen that was in a shell turned into helium. And there's still hydrogen on the outside of all of this in a shell. So now, when the carbon core is depleted, the star collapses like it did before. Temperatures go up until neon core ignites. Neon core starts burning. Carbon shell burns. Helium shell burns. Hydrogen shell burns. Now, what does hydrogen burn into? Helium. What does helium burn into? Carbon. What does carbon burn into? Neon. And so what does neon burn into? Let's see. Oxygen. So now when neon is gone, the star collapses until oxygen in the core that was left over by neon starts burning in the core. Then the carbon shell is turned into neon, that starts burning. The helium shell turned into carbon, that starts burning. The hydrogen in the outer shell now turn into helium, it starts burning. And there's still hydrogen on the outside that still burns in the shell. So we got 4 shells and a core all burning simultaneously. The star is getting bigger and bigger and bigger and bigger. Huge thing now, a Beaumont star. So what is oxygen going to burn into? Oh, well, magnesium. So oxygen turned into magnesium core now. Now, what did the what did the neon shell here turn into? Oxygen, and then carbon and turn into neon shell. The helium shell turned into carbon shell. The hydrogen shell turned into helium shell. And there's still hydrogen on the outside burning. So now we got 1, 2, 3, 4, 5 shells and a core burning simultaneously. This is more like an onion. In fact, they call it onion core. So what do you think is going to happen next? Well, what's magnesium burn into? Well, magnesium burns into silicon. Now remember, silicon is what the Earth's surface is made of. In fact, most of the Earth's surface is silicates, silicon with something else, like silicon with oxygen and aluminum. Aluminum is also the #1 element on the surface of the Earth. And it's all made right here. We're making all this stuff here right now. So we have a silicon core again, oxygen turned into magnesium, and neon turned into oxygen shell, and carbon turned to neon shell. So all of these shells are now burning simultaneously with a silicon core. Now, this stuff now has different time scales. Silicon is burning in 1 day. So this is only going to last 1 day. That's not very long. So this is only good for 1 day. The magnesium is, I think, like 6 months. Oxygen, like a year. So they're burning really fast now. It's not like hydrogen burning for billions of years. We're talking about just a few thousands of years here, goes through the whole thing, right? Although hydrogen and helium take a long time. Now, silicon is going to burn into iron. And this is the very last core. This is the final core, right? This final core has iron in the very center in the core. And it's inert. It's not going to burn. In fact, iron is never going to burn. And there's a reason for that. I'll explain that in just a second. And we have all these shells here. So we have 7 shells: silicon shell, magnesium, oxygen, neon, carbon, helium, and hydrogen. So all you need to do to understand all this and remember it is to just look at these little letters here and try to remember. Hydrogen means H. He is helium. C is carbon. Ne is neon. O is oxygen. Magnesium is Mg. Silicon is Si. And Fe, ferrous, right, is iron. So this is it. This is the final core. All right. Well, before I go any further, I want to tell you guys a real quick story. This real story, it has to do with corn in like Kansas and Missouri. In Midwest, there's a lot of corn. And so farmers in Midwest used to get money from the government not to grow corn. If you're old enough, you remember. So yeah, they used to get money not to grow corn because there was an abundance of corn. Well, the government said, why don't we have the farmers in the Midwest grow the corn, and then we can boil the corn and get ethanol, alcohol out of it. We can put the ethanol, alcohol in the cars, and then we can have the farmers, instead of just getting money not to grow corn, let them grow corn. We'll boil the corn into alcohol, and then we can put it in our cars. So right now, I don't know what percentage exactly. I think it's like 7% of the gas that you pump is ethanol. So ethanol is mixed in with the regular stuff. You can't just put it in any car, but the new cars are all have, ability to burn gasoline and ethanol. Well, here's the problem. The problem is you use more gasoline to make ethanol than if you just put gasoline in the car to just burn gasoline instead of putting ethanol in it. So basically, we're just wasting money. But there's only one benefit. The one benefit is that the farmers get money to actually make corn. That's the only difference. But it's kind of like, useless as far as, the environment is concerned. Okay, ethanol is great, but we're actually using more gasoline to make ethanol to make a clean environment. So we're actually dirtying the environment more by doing this. Well, now that brings us to iron. You can fuse iron. So yeah, you can fuse the iron. But there's a problem. The problem is that to fuse iron, you need to put in energy. So what good is it if you put energy into fusing iron to get energy out of fusing iron? So iron fusion is useless, kind of like making, ethanol to save the environment. So this is bad. This is bad for the star. When this stage is reached, the star is going to cry. Well, actually, I don't know if the star is going to cry, but it's Bob the Builder, right? So Bob the Builder at this stage goes, uh-oh. And this is just a core. The star itself is humongous, right? It's gigantic. So now it's going to collapse. And this is a very final collapse. This is the very last collapse it's going to make. During this collapse, the core will collapse first. So we actually call this a core collapse supernova. We're going to make more energy now, than the sun will make in its 10 billion year lifetime, which is amazing because the sun is making so much energy right now in 1 second. Imagine how much energy the sun makes in a lifetime of 10 billion years. So, how do we do this? Well, what happens is the core collapses. The core collapses is kind of like if you live on the second floor of a building, the floor collapses. It's more like the coyote in the cartoon. Something always collapses and he goes, uh-oh, he goes down, right? So when the core collapses, the upper layers, the rest of this red supergiant goes, uh-oh, there is no floor. The core is gone. There's no support. So the entire star comes crashing down onto the core and it ricochets off of the core. This ricocheting off the core is, a collapse, but then it's going to be an explosion. So it was an implosion followed by an explosion. This is called a supernova event. So a supernova event is a core collapse at first, then the entire star comes collapsing down, ricocheting off of the core in just a few minutes, maybe 5 minutes or something ridiculously short. Ricochets off the core. Tremendous amounts of energy are going to come by this ricocheting and explosion. Like I said, more energy is going to come than anything else happening in the universe since the Big Bang. It's something like 200 billion times more energy um, than the sun. Incredible, right? 200 billion times the sun's energy comes out in just a couple of minutes. So there's going to be this huge explosion. Now, this is something I was just going to give you to see what happens on all these shells that we just talked about. We said the first shell, hydrogen burns into helium. All right, fine. Second shell, helium burns into carbon. All right, fine. Now the third shell, carbon burns into oxygen, neon, and magnesium. So there is this other stuff that's going to come in when you have an iron core. Fourth shell, you have neon burning into oxygen and magnesium. Then oxygen burning gives you not just silicon, but also sulfur. And then magnesium burning also gives you sulfur and silicon. And then silicon burning just gives you iron, just so that you know. Now, here's some of the time scales. Carbon takes 600 years for the carbon core to go kaput. Neon burning takes about a year. Oxygen burning about 6 months. Silicon burning in 1 day. So now we have silicon burning done. We have an iron core. Everything is coming down to ricochet off the iron core. Our core is collapsing. So here's about the size of the core. If you compare it to the supergiant, it's negligible. It's like a tip of a needle here, right? It's like nothing there. Tiny little core. This is our tiny little core, and it's collapsing. The rest of the star is coming down. And so the core is about 10,000 kilometers, which makes it about 7,000 miles. That's not very big. Let's say it's about the size of the Earth now. That's a pretty small core, right? So in fact, really big stars have a smaller core as compared to their size as the sun does to its size. So now, excuse me, this thing is 1.6 billion kilometers in diameter. The core is only 10,000 kilometers, right? All hell is gonna break loose. This ricochet is going to make the stuff that was the superstar, supergiant star, is going to come out something like 70%, 80% the speed of light. This matter is coming out incredibly hot. Temperatures are going to rise to, maybe 100 billion degrees, maybe 1 trillion degrees. At these kind of temperatures, we make the rest of the elements. Like as an example, uranium is going to be made here. Silver is going to be made now. Lead is going to be made now. All those heavy elements are now going to be fused at the time of the supernova explosion. And that may explain why there is so much iron on the Earth, but not much silver, not much gold, not much uranium, because the heavier elements than iron, they're only made at the very end, just for a few minutes. So that explains why there's so much more lighter material. This is an example of a supernova explosion. And when we look at it, every year it gets a little bigger. It's a remnant of a supernova that happened in the year 1054. So about 1020 years ago, this baby went off. Native Americans saw this. There's cave drawings because it was right next to the crescent moon. There's cave drawings of this event. It became so brilliant that you could read newspapers at night. The Chinese astronomers, they have records of it. In Europe, not a single record have been found. I'm sure there's some records, but they haven't been found yet. We're talking about dark ages, 1,000 years ago. So there was so much war and misery. People really didn't care about astronomy back then, you know? They saw a star, they go, it's just another sign that somebody's going to attack us and kill us. Or some disease is going to come and kill us, you know, something like that. This is called the Crab Nebula, C-R-A-B, as in crab that you eat, you know, crab legs. So the Crab Nebula is the most famous supernova remnant of all time. And this kind of supernova, the one that has a core collapse, is called supernova type 2. The supernova type 2 is the one that is making all of these heavy elements. In fact, all these colors mean something. Like the green color here is oxygen. Some of this yellow stuff is sulfur. Some of this blue stuff is nitrogen. Some of this...
Professor?
Yes?
So these are all in like a gaseous state?
That's right. Yeah, these are strands of gas moving away from this, you know, from the explosion.
So this is like what it currently looks like sitting in space?
Yeah, except it was a lot smaller, like this small when it exploded. Now it's about this big. So this is since 100 years ago. When we took images of it, it's actually grown in 100 years. So we can physically see things growing in time. Hubble Space Telescope has only been active for like 20 some years. And when it takes pictures of it, you can see changes. You can see physical changes on the Crab Nebula. And in the very center of the Crab Nebula, there is this exotic object that's called a pulsar. It's a neutron star. We also call it a pulsar. It's a very special star. It rotates about 30 times a second. 30 times a second is pretty incredible. And it's about the size of Brooklyn, New York. It's about 10 miles across. It's about the size of El Cajon. It's about the size of Chula Vista. It's about the size of San Diego. Tiny little thing. The core of the star has collapsed to an incredibly dense state where 1 teaspoon of this stuff is a billion ton. 1 teaspoon, like a sugar cube of this newly formed star we call a neutron star, is a billion tons. That's how dense this baby is. And it blinks at us 30 times a second. It goes blink, 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 30 times a second blinks, right? It was discovered by this student, was working at Cambridge Observatory, and she saw with a radio telescope in 1967, I believe. And then later on, I don't think Mina is going to like this. Later on, a Nobel Prize was given for the discovery of this object, right? The Crab Nebula pulsar, the Crab Nebula neutron star. And the guy that actually got the Nobel Prize wasn't the lady that discovered it, who was her thesis professor. He got the Nobel Prize for it, which is totally unfair. In fact, I've heard so many astronomers complain about this. I'm one of them. why didn't she get the Nobel Prize? Why did this guy get the Nobel Prize? And the guy actually has a Sir in front of it now. Sir, was it Sir Edmund Hewish? That's the guy that got the Nobel Prize for it. Ridiculous, right? Women just didn't get any respect back then, I can tell you that.
What
All
was
right.
the name of that star? What kind of star was it?
A neutron star. I'm going to show you a little movie of the neutron star in just a second. All
Could
right,
you
so
tell
let's-
us the mass again of the 1 teaspoon or the weight or whatever?
Yeah, 1 teaspoon is 1,000,000 tons. A ton is 1,000 kilograms. Your car weighs a ton. Imagine 1,000,000 cars will be a teaspoon of this material. I'll explain to you what it's all about in just a second. Let's just take a look at all this stuff here. So all the elements that you see on the periodic table, they're made either in a red supergiant star, Bob the Builder, right? Or they're made during the supernova, right? So all of these elements here are made. There's the aluminum. Aluminum is the #1 element on the surface of the Earth. And if you remember what I just showed you, you should realize why the Earth is the way it is. Because the cloud of gas that formed the solar system was formed from something of what I just showed you, supernova remnant. And so there was a lot of silicon in it, there was aluminum in it, there was sulfur in it, there was chlorine, there was a lot of iron in it, magnesium, this is manganese, chromium, all of this stuff is plentiful on Earth. #1 metal on the surface of the Earth is aluminum. Iron sank to the core. Silicon is what the Earth's surface is like. We call it silicates. Almost everything on the surface of the Earth is silicates. So that's the Earth, basically, up to here. Beyond that, this stuff is more expensive, like nickel and copper. Copper just sells for a lot of money per pound. So all of these elements are rare now. You know, we're talking about silver, gold, platinum, iridium, all of this stuff, uranium, all of these things are made during the supernova explosion because the temperatures were high enough for elements to fuse to heavier and heavier material. So Bob the Builders built everything that you see here. Now, this is so elegant, right? It's almost like pre-planned, right? Like, let's make a universe that is going to do this. Let's have these stars, make all the elements, and there's a limit to the elements. This is all the elements are possible. Nothing else is possible. Even these elements are not real. These are made inside the laboratory. So don't even count on these to exist in nature. And so the rest of them is what's made, right? Now, I'm not a religious person, but sure enough, man, I think there's got to be some higher intelligence involved here, right? Everything is so perfectly pre-planned. It's unbelievably, fantastically pre-planned, To me, it's like, oh my God, it's all a miracle, the whole thing. So Bob the Builders did it. All right.
I'm sorry, could I get clarification?
Of course.
You indicated there are 2 events that create all of this stuff. It was the supernova and then what else?
Just during his lifetime, right? It made the iron core, it made the silicon core. It made
during the evolution.
Right. Just during those millions of years that it took for it to become ready for a supernova, all the stuff lighter than iron were fused together.
Okay.
Everything heavier than iron, like from this element number 26 onward, everything was made in just a few minutes. Before that, it took a long time for all these other elements to be,
And that was only from red supergiants?
Yes.
Thank you.
Professor,
Only red supergiants have enough temperature. Yes, please.
I feel like this is a dumb question, but like
Oh,
I
love
don't.
those questions. Yay. Please.
Okay, I don't understand. So all of the silver and elements that are in our Earth come from a supernova that
Exploding.
is somewhere like far away in the
No,
galaxy, or
they're
just
made-
from
they're
like the big
made
one?
before the sun, right? It was in our galaxy. So this is a sun's poppy, the father of the sun. Yeah, she's mother of the sun, whatever you like, right? So they were made prior to the solar system forming. When this started, made all the elements that you're made of, I'm made of, everything you touch is made of. All these elements came out in the form of supernova remnant, and then this cloud of gas, it later on coagulated to make the sun and the rest of the solar system. So all the planets, the sun itself, it all came from the remnants of a supernova. Are you with me?
Then when the supernova.
So it wasn't a stupid question at all. It was a very good question, actually. What's your last name? I'm going to give you a point for that.
Larcomb,
You spell that.
Larcomb.
Okay. Thank you very much for the question. Excellent. Thank you.
Thank you.
Now, when the core collapsed, right? Remember that core was collapsing? When the core collapsed, this core collapse continued. It didn't stop. It continued. And it continued and continued until the neutron star formed. Now, how did the neutron star form? Well, as this thing that was only 10,000 kilometers across was collapsing and collapsing, density went to crazy levels. In fact, it went to where the electrons did not have enough room to exist. So the electrons and protons, because there was no room for them to exist, the electrons entered the protons. This is amazing, right? They entered the protons to make neutrons. And so the protons inside, they became neutrons about the size of 10 miles or so, about the size of San Diego. And that's what a neutron star is, right? Let's take a look at it real quick. I have a little video for you guys to see what the neutron stars. Now, how do I stop the sharing here? Let me stop the sharing. I want to share this movie with you guys. There goes my movie. Okay, there's no sound on this movie. Can you guys see the star here? Now you can write this down. Can you guys see the star? Somebody say yes, please.
Yeah.
Thank you. I don't see anything right now. I'm blinded here. So let me see. Why am I? You guys can see it says pulsar visualization.
Yeah.
Okay, great. Sheesh. All right, now this is the star. It's a neutron star. It's made of neutrons. It's like a big ball of neutrons, right? Remember, neutrons are just like protons. They just have no charge. Now, this thing here is rapidly rotating. When it's first made, it's probably rotating 1,000 times a second. A second, I tell you. The one in the Crab Nebula is rotating something like 30 times a second now. So they slow down. Over time, they slow down. They have a fantastic magnetic field, amazing magnetic field because they're fast rotators. And this magnetic field has like a north magnetic pole, south magnetic pole. So let's just take a look at it for a second. I'll stop when I see I can show you guys more like this. This magnetic field is like 10,000 times, a million times, 10 million times sometimes stronger than the sun's magnetic field. Remember, the sun's magnetic field is millions of times stronger than the magnetic field of the Earth. So these are amazing magnetic objects. In fact, some of them are called magnetrons. They're fantastically magnetic, the most magnetic objects in the universe. So now, from the north magnetic pole and the south magnetic pole, electrons get caught up and they spiral around these magnetic lines of force, just like what I'm showing you here. You see this, my cursor is spiraling. And as they spiral, they lose energy. Electrons lose energy. So they give up energy. This is called synchrotron radiation. And I'll spell it for you, synchrotron. S-Y-N-C-H, syn, S-Y-N-C-H-R-O-T-R-O-N, synchrotron. So synchrotron radiation is when electrons get caught in the magnetic field and they lose energy. So energy comes from the poles here. Energy comes from the North Pole, energy comes from the South Pole. Now, if you happen to be lined up with a North Pole or a South Pole of a neutron star, you see this neutron star pulsing at you like a lighthouse. So when you see a star that is a neutron star and is rotating and you can see it get brighter and faint like a lighthouse, we call that a pulsar. That's what a pulsar is. Pulsar is a neutron star that the Earth happens to be in the lined up with the north and the south magnetic poles of. Now look at the rotational though. Rotation of this is not lined up with the magnetic poles. So look, there is the rotation here. This is a north pole, south pole, and this is a north magnetic pole and south magnetic pole. So if the Earth is lined up with a north magnetic pole and a south magnetic pole, we see a pulsar. If not, we just see a neutron star. So far, more than 10,000, I think something like 50,000 now, more than 50,000 pulsars have been discovered. So there's lots and lots of them. These are all remnants of supernova explosions. So supernovas happen once every about 300 years in a galaxy like the Milky Way. The last time it happened was when, remember that guy that we talked about, Tycho Brahe? The guy that drank so much beer, his tummy exploded? That guy, he saw the last one that we saw on Earth more than 300 years ago. It was more like 400 years ago. So we're due for a supernova explosion any day now. Hopefully you will see one in your lifetime. When you see it, it will light up the night sky. If it's within 100 light years, it'll destroy the Earth. Everything on the Earth, all the life forms on the Earth, within 100 light years, it'll destroy that. But there's nothing that is going to go supernova within 100 light years of the Earth. So we can be fairly secure in knowing that. But still, you know, they're very, very dangerous things, these supernovas, if they go off anywhere near the solar system. All right. Now, if the star, let me see if I can kill this. If this star that we call a pulsar, let me go here, shrinks down to the size of San Diego, is tiny, right? Why does it not continue and become a black hole? Because black holes are basically the same thing after the supernova. If the core of the star has more than 3 times the mass of the sun, it will continue to collapse to become a black hole. This is where black holes are born. Black holes are born from a red supergiant's evolution. That's how black holes come to be. But now, if you have more than 3 times the mass of the sun, it's going to become a black hole. We'll talk about black holes next time. It's going to be all black hole. But this time, I tell you, Pauli exclusion principle stopped the collapse of the neutron star. Now, what the heck is a Pauli exclusion principle? Basically says that no 2 protons, no 2 neutrons, no 2 even electrons can exist in the same place at the same time. So if they do, it's kind of like somebody sitting in your chair. I'm sitting in my chair right now. My son can't come and sit in this chair. I'm not, it's not allowed. That's the Pauli exclusion principle. It's a law of nature. No two particles can occupy the same space at the same time. To really say it correctly, no two particles can occupy the same quantum state at the same time. This is the Pauli exclusion principle. Very simple, right? So please try to remember that, this Pauli exclusion principle thing. What time is it? Still got time. Great.
So would you put that back up, please, just for a sec?
Sure. Now, if you have more than 3 times the mass of the sun, the universe is going to tear up a hole in space. That's what a black hole is. Black hole is a tear in space and time. So you're going to break the Pauli exclusion principle. You're going to break the fabric of space and time.
Thank you.
You're welcome. All right. Let's finish this now. Okay, let's see. What's what here? I think it's over here now. I don't know what I'm not doing anymore. Okay, that's good. Yeah. All right. So now these are some of the time scales. How long does it take O stars, B stars, and A stars to evolve, right? So here are the numbers. O stars last about 5 million years or less, and they evolve. That's why I said you can't have life forms around them, because life takes a long time to form. 5 million years is just not long enough. And so O stars, definitely not life forming. Intelligent life, forget about it, at least from what we know. B stars, same thing. They only last for like, maybe a maximum of something like 50 million years, 60 million years. That's it. So again, B stars are also Bob the Builders. These are all Bob the Builders. A stars can last up to 500 million years. So an A9 star, the coolest of all the A stars, it can last up to 500 million years. F stars and G stars, they can last for billions of years. Now, the sun is going to last for 10 billion years on the main sequence, which is stable, right? Everything on the main sequence is stable. So G9 star, even longer, right? Maybe 100 billion years. M stars, 500 billion years. M9 stars, probably trillions of years. So the more mass you have, the faster you evolve, and the more volatile you are. So these O and B and A stars, I call them Bob the Builders. They're in charge of building all the elements in the universe. They build the entire periodic table of the elements. The F, G, K, and M stars, much more stable. These guys are the Mary Poppinses of the universe. These guys don't become anything dangerous for a long, long time. So even intelligent life can form and ask questions like, how long do G2 stars last on the main sequence, right? So now the sun type stars become subgiants and then giant stars. And then eventually they're going to turn around and come around here, build those cocoons called the planetary nebulas, and they become white dwarfs. White dwarfs are going to go down and become black dwarfs. They exit the main sequence to become black dwarfs. Now, O stars and B stars, they go up and to the right. They're going to become red giants here, red supergiants. So these red supergiants are made from O, B, and A stars. And so these guys move like this. Basically, they move into this area of a supergiant. This is area 1. And so luminosity class 1, luminosity class 3, and luminosity class 5. Now the rest of these also have luminosity classes, but since I might give you some of these on the exam, so I'm not going to give you guys more than just 1, 3, and 5. Like white dwarfs are luminosity class 7, like that. So I'm not going to get into that. All right. More massive stars evolve quicker. More massive stars are also more luminous. They make more energy. So the more luminous stars also evolve quicker. So what stars do you see in the sky when you look in the sky? These are the skies. That's what you see in the sky. You see supergiants, you see giants, you see O stars, B stars, and A stars. How about these guys here? You don't even see these. If you go away from the sun, 10 light years away from the sun, you won't even be able to see the sun. So surrounding us, there's a lot of these little tiny stars, these little tiny M stars. We'll talk about that later. All right, now Pauling exclusion. This is the size of a neutron star, city size basically. This is Vancouver. I don't know. And then we said a pulsar is a neutron star that the Earth happens to be at the very end of the north or south magnetic pole. So the Earth has to be lined up with it to become a pulsar. So we can have the lighthouse model. As it rotates, we see a pulse. Oh, pulse. And then no pulse, then a pulse, then a no pulse, then a pulse. So it's like a lighthouse as it rotates. All right, finally, we have everything put together. This is the entire star life cycle. These are the stars that are less massive, like sun-type stars. They are protostars, remember? And these protostars become main sequence stars. Main sequence stars like the sun, they become red giants, they become planetary nebula, they become white dwarfs, eventually a black dwarf. So there's the entire evolutionary track of sun-type stars like that. If they don't have enough mass, they become brown dwarfs. Remember that? Brown dwarfs are the ones that don't have any fusion. If they have more mass, then they go here. More massive stars, they become red supergiant stars. Then they go supernova. So sun type doesn't go supernova. After supernova, they become neutron stars. Some of neutron stars are pulsars. And also, they become black holes. So we haven't talked about that yet. We haven't talked about black holes yet. And we haven't talked about white dwarfs in a binary system. Because if you have a white dwarfs in a binary system, it's possible to make a supernova differently. It's called supernova type 1a. So supernova type 1a is another kind of supernova that we'll talk about later. And just for the sheesh of it, I'm going to show you guys the sizes. Here's the size of the sun. Sun is about 800,000 miles across. This is Betelgeuse. That's the red star in the constellation of Orion. It's the brightest one in Orion. This is how big it is. This is an O star. Rigel is an O star. So you can see how many times bigger than an O star it is. O stars are big, but nothing like this. This is the brightest star in the sky that we see right now. It's an A star. So look how tiny A stars are. This is a red giant. Red giant, O star, red supergiant, and the sun. And these are little tiny M stars and K stars and stuff. Insignificant. It turns out, though, that most of the stars in the sky are little tiny M stars. In fact, 90% of the stars are M stars and K stars, little tiny nothings. And we can't even see them. The closest stars to the Earth are not even visible because they're so tiny. So the stars that you see in the sky, they're all these stars. They're red giants, blue stars. Sirius, brightest star in the sky is an A star. These are what we see in the sky. We see evolved stars, we see O stars, B stars, and A stars mostly. Most all of them. All right, I'm done, you guys. I'm done. My tongue is dry as a sheesh. And